Let me explain what is Neyman-Pearson's lemma. In the hypothesis testing, before Neyman and Pearson came up with their paradigm, there was this approach called Bayesian approach. In Bayesian approach, what we find is posterior probability ratio, and we check whether if it is greater than 1, if it is greater than 1, we say H0 is plausible. If it is less than 1, we say H1 is plausible. And to get a posterior probability ratio, we need to know both prior probability and likelihood ratio, since it's a product of prior probability and likelihood ratio. What it means in terms of hypothesis testing is, if we have to do hypothesis testing, we have to know both prior probability and the distribution of H0 and H1 to obtain the posterior probability ratio. That's when Neyman and Pearson formalized their theory in hypothesis testing as a decision problem. What it means is, they wanted to say whether we accept H0 or reject H0 based on a critical value under significance level alpha. So what their lemma says is, the smallest likelihood ratio, which is less than a critical value, at the significance level alpha, which accepts H0, is considered as the most powerful test. Any other test either has less power or equal to that of our likelihood ratio test. What it means in terms of likelihood ratio, what does smallest likelihood ratio it means? It means if we take a sufficient statistic of our likelihood ratio, and if we try to make it the smallest, let's say if I take x bar, and if I say x bar makes my likelihood ratio smallest, then I should consider that against my critical value. Let me show you an example. Let's take random variables x1 to xn from a normal distribution with a known parameter sigma square. Sorry, known variance sigma square. And this is the likelihood formula, and this is the likelihood ratio. And once I try to find the sufficient statistics, I end up with this. This calculation is available in almost most of the websites that talks about Neyman-Pearson's lemma. And there are two cases in this, when mu0 minus mu1 is greater than 0, and mu0 minus mu1 is less than 0. If you look at this statistic, when mu0 minus mu1 is greater than 0, x bar has to be small because it gets multiplied with that. Again here, when mu0 minus mu1 is less than 0, x bar has to be large to make the likelihood ratio small. So let's take the case 2. I mean, we can do it with either case 1 or case 2. Let's take case 2. By case 2, x bar has to be large against some value. With this, we can call it as a critical value to get the alpha. So when I standardize this, finally I end up with this formula. So this is a short introduction into what is Neyman-Pearson's lemma. And one more positive with Neyman-Pearson's lemma is, you don't have to know prior probability, and you don't even have to know the distribution of H1. Distribution of H0 in most of the case is sufficient to do a Neyman-Pearson's test.